Alright, hello everybody, and in this video I want to talk some about another piece of stoichiometry. We've talked about stoichiometry a few different times so far. This is simply stoichiometry involving gases. Alright, and the way we're going to approach things is really very similar to what we've seen before. Whenever we talk about a chemical reaction, we have a ratio, a molar ratio, in this case 2 to 4 to 1. Alright, so we talked about molar ratios with solids and liquids and aqueous solutions and things like that, and with gases it's exactly the same. If we want to convert from one thing to another, if we want to figure out grams of this from grams of this, we need to go through moles. Alright, if we want to figure out grams of this from grams of this, again we need to go through moles. Now with gases, we can actually have a slightly different approach to how to get to the number of moles, simply because of the fact that we have seen in the gas laws chapter a way for us to calculate moles of something by, of course, the ideal gas equation. Alright, PV equals nRT, you guys have seen that before. So let's take a look at the question here. It says, in the above reaction, 4.58 litres of oxygen was formed at a pressure of 745 torr and a temperature of 308 Kelvin. Alright, and you know what, I realized I haven't added the rest of the question here. Bollocks, let me add that on. So the rest of the question really should have stated how many grams of silver oxide must have decomposed. Alright, this is a decomposition reaction where we go from one thing and we get two things out. Alright. You can also just say how many grams of silver oxide must have reacted to give all this oxygen. Now, you guys know that the only way to get to grams of something is if we had moles of that thing to begin with. Alright, so the only way to get to grams of silver oxide is via moles of silver oxide. So we need moles of silver oxide if we want to get to grams of silver oxide. And if we want to get moles of silver oxide, we have to have moles of something else. In this case, moles of, I suppose it's oxygen. We're given a bunch of information about oxygen, so if we can figure out the moles of oxygen that we have, we can take that, convert that moles of oxygen to moles of silver oxide, and then convert the moles of silver oxide into grams of silver oxide. So the question then becomes, how do we calculate the moles of oxygen? Well, look at the information we have. We have a volume, we have a pressure, and we have a temperature. Volume, pressure, temperature. We know what our R is, that's always a constant, now 0.082 litre atmospheres per mole per Kelvin. N is, of course, then what we can calculate. Once we know N, that's our number of moles of oxygen, then we just follow this route to get to our answer. Alright. So, any unit conversions that we have to do here before we do anything else? Of course, yes, we have to convert our pressure into atmospheres. Alright, so we know then that 745 torr, if we wanted to write that in atmospheres, we just have to remember that we have 760 torr in 1 atmosphere. And that gives us 0.980 atmospheres. Then all we're going to do is plug everything in. So our N is equal to PV over RT. Alright, we know our pressure is what we just calculated. That's 0.980 atmospheres. I'm going to miss off the units here simply so I don't run out of space. We have our volume that's already in the units we want, 4.58 litres. Then on the bottom we have our 0.082 with its own units, and then our temperature of 308 Kelvin. We calculate all that out, and what we get is 0.178 moles, in this case, of oxygen. Alright. Now, let's just follow then the path that we said we were going to follow. If we have 0.178 moles of oxygen, We look up at our balanced equation here and we know we have 2 moles of silver oxide for every 1 mole of oxygen. And to get to our grams of silver oxide, we just need the molar mass. So we have our 1 mole of silver oxide here to cancel out with our moles of silver oxide up here. Calculate that out, and what we get is 231.74 grams of silver oxide in 1 mole. And what that gives us, all right, cancel out moles of O2, moles of silver oxide, we get out our answer here. And what we get is 82.5 grams of silver oxide. That's the amount of silver oxide that we must have had to begin with. It would have decomposed to give this much oxygen. So that's a simple example of how we'd use stoichiometry involving gases. You can see we have to convert to moles given whatever information we have, and the ideal gas equation is what's needed. All right. In some cases, you might have to do something like, for example, 1 mole of whatever gas you're talking about is equal to 22.4 liters that we talked about. Oops, that's a 22.14. Oops, indeed, I guess. 22.4 liters. There might be some questions where you've got to use something like that, but in most cases you'll be using the ideal gas equation like we did. And that's how gas phase stoichiometry works. Alright, thank you.